Hello there. Today we'll enter in chapter 5, which is the probability chapter, and we'll cover page 39 up to 43. So we'll start with random phenomenon. So when something is random, we can't predict the next outcome. However, after many outcomes, a distinct, predictable pattern appears, and this pattern follows the laws of probability. Random does not mean haphazard. It's a kind of order that emerges only in the long run. And we'll see this long run thing and the outcome thing. We'll do an experiment. I'll use this link, which is it generates automatically like heads or tails. So it's a coin toss. You can do your experiment, or you can just follow mine. I will put the link in the description. Let's proceed. We'll start with an example. So in this example, we'll study the concept of probability when tossing a fair coin. A fair coin is a coin which isn't made in a specific way to get more heads than tails. So the probability of getting head if we toss a fair coin will be the same as tails. So the answer here, what's the probability of getting head if we toss a fair coin? It's 1/2 or 50% or 0.5. 1/2 because our desired outcome is the head, and the total outcomes are like head and tails. That's why we use the 2, but yeah. You can say 50% as well, and you can use that web link. So after going in the website and flipping my coin, I got a tail after one flip, like toss. And what the proportion of heads obtained in all your tosses so far is 0/1, because we had only one toss, so in the denominator is the total amount of trials, and 0 is we had none, right? So 0 head in one toss. Is this close to the probability of heads you expected? And why? No, it isn't close, because we were expecting to be like 0.5, which is 30%, and which is called like true probability too. So the reason is because we only tossed it like once, right? We need more like experiment trials. Then I'll flip the coin 9 more times. So in total we flipped it 10 times, right? What's the result? So I got 4 heads and 6 tails in the 10 total tosses. And the proportion of heads obtained in all your tosses so far is 4 heads, and the denominator is the total flips, right? Which is 10, or 4 plus 6 equals 10. So the proportion is 0.4. Yeah. And the question is this close to the probability of heads you expected, and why? It's closer to what we're expecting, which is 0.5, but we will need more, even larger number of flips, right? So let's proceed. So in that web link, there is a way you can like flip the coin 1,000 times. So the result was very close to, the proportion was very close to 0.5, because I got something like 400 something heads and 600 tails. So it's closer to 0.5. So this is what we're expecting to go closer and closer to the true probability as we increase the trials, right? And probability quantifies long-run randomness. Probability of an outcome of a random phenomenon is the proportion of times the outcome will occur in a very long series of independent trials, which is what we did, right? Probability is a long-run relative frequency. Computer simulations are useful for pretending we are performing an experiment a very large number of times, which is, I used the computer simulation, right? Independent trials. The outcome of any one trial is not affected by the outcome of any other. So, for example, if I flip a coin now, and then I flip the coin again, these two like trials, it will be like independent. But on the other hand, if we play like blackjack, it's not the same way because we are removing the cards, so it's different, and we'll see an example. And then why do we need probability? Probability is used in many areas: gambling theory, gaming theory, queuing theory, investments, weather patterns, etc. This is statistics course, so we'll study some simple examples of probability that will help us to understand the sampling distribution of statistics and statements we make in statistical inference in the next chapters. Subjective probabilities are some necessary when there is no long series of independent trials. They are determined using all the information available. And there are some concepts like definitions. So sample space is defined as the set of all possible outcomes. And so if we flip the coin, for example, flipping the coin once, the sample space is head or tail, right? And event is an outcome of group of outcomes, and so it's a subset of the sample space. So for example, a subset of sample space is the head, right? Getting a head is an event, right? Probabilities are between 0 and 1. This happens, I mean, when the probability is equal to 1, it means that it will happen, right? And when it's 0, or it goes towards 0, the chances of happening, the chances of an event of happening decreases, right? And the minimum number is 0 when there is no chance of that event occurring. And the other thing is the sum of all outcomes probabilities must be equal to 1. So if this isn't like in an example, if we sum all the outcome probabilities and it isn't equal to 1, then we probably done the wrong calculation, and we'll see in examples now. So this is the second example, and we'll write down the sample space and the probability of each event. So the question 1 is like toss 2 coins and record the number of heads, and the other one is about like dice, and we'll see now. So if we toss 2 coins, coin 1 and coin 2, and we'll record the number of heads. That's our goal. So first of all possible outcomes when you toss 2 coins, for example, coin 1 and coin 2. So we can have head for the coin 1 and head for coin 2, right? Then like this is like one case, right? Then we can have head for coin 1 and tail for the second, right? Then another outcome is tails for the red coin and head for the blue one. Then the last one is tails for both. So we have like four like possible outcomes. And regarding in this experiment, we are interested in the number of heads, right? Because the question says record the number of heads. So the possible outcomes for head, how many heads we can have, is like 0 heads, which is this scenario, 0 heads. When we are in 1 head is this one and this one, or 2. So the sample space is the number of heads that it's possible to have. It's 0, 1, or 2. But these in this example aren't like equal likely. So to find the probabilities, we'll use the outcomes, the possible outcomes, which are equal likely events. Now we'll like calculate the probabilities. So the probability of getting 0 heads it's equals to the number of ways we can get 0 heads. Can you think like over here which like how many is the number of ways that we can get 0 heads? So here we have 1 head, here we have 1 head, here we have 1 head. The only way is if coin 1 and coin 2 is like tails, otherwise we won't have like 0 heads, right? So here it's going to be this 1, and the number of all possible outcomes, it's 1, 2, 3, 4, right? It's all the possible outcomes. So the probability of getting 0 heads is 1 over 4. Now after this we'll go and calculate the probability of getting 1 head, which will be different. So again, the probability of getting 1 head this time. So the denominator is the same, right? The number of possible outcomes, it always remains the same. But now the number of ways we can get 1 head, you have to pause the video and think. So in the total possible outcomes, the cases where we have 1 head is this and this, right? These two. So we have 2 number of ways to get 1 head. It's either coin 1 is going to be head and or coin 2 is going to be head, right? So here coin 1 is head, here coin 2 is head. So it's 2 over 4. Now we're going to calculate the same thing, but this time for the probability of getting 2 heads. The denominator is again the same, and can you guess what's the number of ways you can get 2 heads? Which out is this outcome? So it's only one way, right? One way. So it's 1 over 4. And then, if you remember, we said that the sum of probability of all outcomes must be equal to 1, otherwise we've done something wrong. So if we sum the previous probabilities we calculated, probability of getting 0 heads, probability of getting 1 head plus probability of getting 2 heads, it will be 4 over 4, so it will be 1, so it's correct, right? Also, now we'll go in our second example. We'll roll a balanced die and record the number of dots on the up face. So this experiment is easier because we don't have two things. We only like measure the die, one die. So the sample space is the number of dots that we can get, right? So it's like either 1, 2 dots, 3, 4, 5, 6, right? That's all possible like outcomes that we can have. And these are equal likely events. So they're all 1/6, right? We have 6 sides in the die. And then we also like calculate that their sum is equals. We add their sums, 1/6, 1/6, 1/6, etc. It's 6/6 equals 1. The sum of all outcomes probabilities is equal to 1 as we expected, right? Now we'll dive deeper, so we'll explain these things which are easy. So the basic rules for finding probabilities about a pair of events. So two events on same trial. This example, rolling a die. Complement. Complement of an event is the rest of the sample space. That is every outcome that is not in A. Everything outside of A. Here, and the complement of A is denoted as A, this C symbol, which is, it means complement. And the complement is equal to 1, which, if you remember, 1 is the sum of all possible outcomes, right? Minus the event of A. So the complement of A is equals to 1 minus event A. And in other words, the complement of A, it means that it's like the event of A not occurring. So if the event A, it's this yellow circle, the complement, it will be whatever is outside of the yellow circle. So it's the red thing. So if we add the yellow and the red, we'll like get 1, because we are adding all the sample space. So whatever is in the square is the sample space, right? If we add the event A and its complement, we'll get A. So if we can like see it here. If we flip this here, we get 1. And the example is A equals, we want to get 4 when we roll the die. And so its complement, it will be whatever exists apart, like so it's the event of A not occurring. So not getting A4, it's either 1, 2, 3, 5, or 6. It's not A, right? And the probability of getting a 4, since the sample space has like 1, 2, 3, 4, 5, 6 values, it will be like the 4, which is like 1/6, right? They are equal, like it's like equal events, equal likely events, right? So each one is 1/6. And this complement, which is the event A of not occurring, will be like 5/6, because 1, 2, 3, 5, 6. There are like in total 5 ways, and the total is 6, right? 5/6. Or we can do something else. We can just use this. Now 1 minus probability of event A occurring, and as you can see, 1 minus 1/6 will give us the same result. Now we'll go in intersection. So intersection of two events A and B is the overlap of the two outcomes that are in both A and B. So intersection has this symbol, the inverse like U. It's the, so if two events A and B occur on a single like performance of an experiment, so this is called the intersection or joint, like probability of A and B, and it's denoted like this. So intersection of A and B is equals to A and B like happening. So probability of the intersection of A and B is equals to probability of A and B, event A and B occurring. And this teal color, for example, if this A, the whole circle is A, event A, and B is this circle, then the overlap, this teal part, the overlap of event A and B is this teal part, right? So let's see the example. So event A is like we get an even number of die, right? Even numbers are 2, 4, 6, or 3 in total, right? And event B is get a number smaller than 5. Smaller than 5, all number like 1, 2, 3, 4. As you can see, 2 and 4 like is here, right? Because numbers smaller than 5 is 1, 2, 3, 4, right? 2 and even numbers are 2, 4. So the intersection will have like 2 or 4, right? Here, because it's like their overlap, right? And the probability, it will be like for intersection is getting 2 or 4, right? So it's like two ways, like there are only 2 ways, so 2 like desired, like the desired outcomes are 2, right? So in the numerator is we put 2, and in the denominator is the total like possible outcomes, which is 1, 2, 3, 4, 5, 6. So it's like 6 different ways. The ways, 2 ways, and 6. So 2 divided by 6. Union of two events A and B consists of all outcomes that are in A or B or both, and it so the probability of either A or B event occurring, it has this symbol, the U, which is like union. So either of them occurring, probability of either A or B occurring, it will be equal to probability of A or B. And in this example, since we have two events A and B which they are overlap, in this example it will be equal to the probability of event A plus the probability of event B minus their intersection. Intersection is over here, right? So in this example it will be like equal to this, right? It's a formula. You have to memorize it or use it, yeah, diagram. So let's go in the example. So A, the event A, we define it as as getting an even number in the die. Even numbers in the die are 2, 4, or 6. Event B, we define it again the same way, actually. Get a number smaller than 5. So this time we want all this area. So we want the event A or B or both happening. So this consists of 2, 4, 6. This consists of everything below 5. So their union will be 1, 2, 3, 4, and also the 6, which is from the A, right? So only one number misses, right? So the probability will be like the number of ways we can get either A and B, which in the numerator. In the numerator, it will be the number of ways we can get the union of A and B, which is 5 ways. It's like these 5 numbers, right? And the denominator, it will be like all possible like outcomes, which is this plus also the 5 outcome, right, which is missing. So one more, so it's 5 over 6. Or as you can see here, let me highlight it. Okay, this is not a good color actually. Okay, this is a better one. And so we used, if you see here, you can see it's like or we can calculate it like this, right? We can like plug probability of event A happening, which is get an even number, which is equal to 3 over 6, because it's 2, 4, 6, 3 ways. Then probability of event B happening, which is everything below 5, which is 4 ways happening, 4 over 6 total, and minus the intersection which we found. So you can either find it this way or like automatically like thinking like the diagram. And now we'll see the disjoint events. If two events A and B have no outcomes in common, they are called disjoint events. For disjoint events, their intersection is 0. So this means that their union here, the red term is 0 this time. So as you can see, we removed it. So their union is like only like the summation of event A happening and event probability of event B happening. So this is when they do not have here like any like common intersection, right? Here they were like intersecting, right? Here they don't. When the events look like this, they are like called disjoint, which means that if like A happens here, I mean they can't happen at the same time, right? So that's why the intersection is 0. And we'll see an example. So this time, actually again, A, it's like the event of getting an even number, which is like the possible ways of getting an even number is either getting 2 on a die, 4 on a die, or 6 on a die. So there are 3 possible ways of getting an even number when we are like rolling a die. And the event B is getting a number smaller than 2, which is there is only one possible way to get some number smaller than 2, which is it is getting 1, so only one way. So their intersection is the empty space, because they don't have anything in common in there, like if 2, 4, 6 or isn't, and doesn't have any like common thing with the 1. So event A and B, they don't like can't happen at the same time, right? That's why their intersection of the events is this symbol, which is the empty space. It's called empty space. And the probability of this event, of the empty space event, is equal to 0. Then the union will be like 2, 4, 6 and or this 1 from here. So 2, 4, 6 are from the event A, right? And 1 is from the event 1. And the possible ways that we can, the probability of A union B, like we can occur, the possible ways are like 4, right? The possible outcome that can make it like happen. It's like either get 2 when we die, when we roll the die, 4, 6, or 1. So in the numerator is 4, and then denominator again is in the total possible like outcomes, which is like when we roll a die, we have like 6 possible outcomes: 1, 2, 3, 4, 5, or 6. That's why it's 4 over 6. But notice we could like calculate this value from here, there, right? You could just put the probability of A in this specific example is 3 over 6, right? Because there are 3 ways of getting an even number, and over 6, which is the possible, all possible outcomes. Then plus the probability of B is the ways that we can get like 1, because the event B it's like smaller than 1. So it's 1 over 6. So 3 over 6 plus 1 over 6 is 4 over 6, right? So it's like a different way to calculate the same thing. Now we'll go into events in the sequential trials. Independence. So this is important. If 2 events are independent, knowledge about one event tells us nothing about the other event. Which means like when we're like doing the tossing, like, and the multiplication rule, this is like important too. If A and B are independent means when something happens, an event happens, it doesn't tell us like anything, like any information about the other event. So if A and B are independent, then A intersection B, which is equal to A and B, is equal to the probability of A multiplied the probability of B. And this only happens when A and B are independent. You can't like use it directly. Be careful. You have to know that they are independent, the event A and B. So never like do this directly. And note that this informal definition is informal definition, but in statistics we usually assume it depends from the way sampling was conducted. We don't check it mathematically. So let's see the example now. Rolling 2 dice. So A is to get a 4 on the first roll, and B is to get 4 on the second roll. So when we like roll the first die, to the probability of getting like 4, it's 1 over 6, because we have in total the total outcomes are 6, and our desired outcome is like the 4, which is just 1, so it's 1 over 6. Then for the event B it's the same. Again, when we roll the second die, again it's the same, right? 1 over 6, because there is only one way to get the 4, like it's 1. So, and the possible outcome is 6. Their intersection here, since event A and B are independent, because knowledge about the event that we in the first roll die we got like 4, this knowledge doesn't give anything like when we want to like calculate P, because it's in like another die that doesn't like change anything. So since A and B are independent, their intersection will be given by the probability of A event A happening multiplied by the probability of B event B happening, which is 1 over 36. So this is P. This is, let me highlight it. So this is this, and okay, I mean you got it right. So this probability of A and this probability of B. This probability of A and this probability of B. So I just use this. So they have the probability of A 1 over 6. We have the probability of B 1 over 6. We multiply it and get 1 over 36. Then now let's assume that A is the probability is the same to get 4 in the first row, but this time B is to get an even number on the second row. On the second row, to get even number, we have to get 2, 4, or 6. So 3 possible ways. So the 3 over 6, because 3 is the possible ways to get even number, and 6 is the total possible outcomes when we roll a die. Again, we do the same. Since the information about that we in the first roll we got 4 doesn't give anything when we do the second, when we like roll the second die, right? This information doesn't like do anything. So A and B are independent events. So again, we use the same formula. Probability of the intersection of probability A and B equals the probability of A multiplied with the probability of B. This with this. So it's 3 over 36. So this example says that grades on very large statistic class are given according to the following distribution. This is the distribution. Find the probabilities below and explain which rules you use to compute them. So first of all, we have the probability of getting A, the probability of getting letter grade B, probability of getting C, D, and we want the probability of getting letter grade F. Notice that no one can get A and B at the same time, or B or C at the same time, or C and D, or A and D, anything. So the events, these 5 events are disjoint. If you go back and see the formulas when the events are disjoint, you will see that their union, the union of A and B, the union of A and B, or the probability of A or B happening, their union, it's equal to their sum, right? So if we take the union, all the unions, it will be like equal to their sum, and it will be equal to 1, right? Because the sum of all events in the disjoint case is equals like to 1. So in order to solve the first question, you use the disjoint thing as the union, right? So we use the union and disjoint event. So we know this is equal to the union of A, B, C, D, F, right? Because they are disjoint events, the union of A, B, C, D, F is equal to their sum, and we know that the sum of all like outcomes, possible outcome, it is equal to 1, right? So we solve with respect to F, and we get 1 minus anything. These 4 terms are here, and these 4 terms actually it is equal to the event F not happening, the probability of the event F not happening, right? But either way, we do the calculation, and it's 0.04, and we use these two. Let's proceed. So the second question asks us, what's the probability that the student gets better than a C? How can a student get a letter get better than a C? It's here, right? Only these two, right, are better than C. So P, probability of A or B, since we know that they are disjoint events, their union, it will be equal to their sum, and we just plug these values, and it's equal to 0.5. And we use the union rule disjoint events, right? And now let's see the next. And the next question is, what's the probability that the student gets a C or better? So this time C is included, right? This time is all like this. So it's the union of A, B, C. So it's the probability of event A or B or C, because they're like C or better. So A or B or C, and since they're disjoint events, the union becomes sum. So we add these three probability events. Over here we have the values. We have in percent, so we put it in proportion. So 0. This, and the result is 0.8. And this this is the union symbol, right? Just the next question, D, it's what is the probability that two randomly selected students which are like independent, this is important, very important, independent of each other, both get an A in the class. And if you remember, since these two events are independent, we can use what? The multiplication rule. And it will be the probability for the student A, for the first student to get A, and the probability for the second student to get A. Since here the yellow highlight thing there, it's 0.15, so 15% for both of them, and since they're disjoint, we use the multiplication rule. So we do the multiplication, and this result 0.0225. And this is only true for independent events. So, and this is like if you don't understand by handwriting, so it's like typed. So it's the same exactly everything. You can pause and check, verify. And now another example, which is with decks. We know that the standard deck has 52 cards, 13 each hearts, diamonds, spades, clubs, and it also has like 4 aces, right? 1 in diamond ace, spade ace, club ace, and heart ace. So we want to know if all cards are independent. So if we draw the first card from the deck, the first card, the probability of getting ace, it's like in the numerator, it's like all possible ways that we can get an ace. Since there only exist 4 cards in the deck with aces, the possible ways are 4, the numerator. The denominator is all possible outcomes. All possible outcomes are all cards in the contained in the deck, which is 52. So this, for the first card, the probability of getting ace. Then if we draw another card, if this first card was ace, then we will have 1 less ace in the total cards, right? So there will be only 3 remaining, because 1 was drew in the first card draw, and that's why it will be 3 on the numerator. There are 3 remained aces, and the numerator, since we drew a card, the remained in the first draw, the remained card, there will be like 51. not 52. But if the first card wasn't ace, then we would have 4 aces still remained, right? But this first card, it would have been like something else, so we would have like one less card, so 4 over 51. And as you can see, the cards aren't independent. Why? Because when this within the first row, this event like because the information of what we draw as first card is very useful of like knowing what the probability of the event of like getting ace when we are like getting our second card. So this information is useful, right? So it is clear that they are not independent because probability of getting an ace depends on which card we have already like dealt. So this is another example. Consider a family with 3 children. Genetics tells us that boy and girl are equally likely, and the gender of each child is independent of the rest. Write all possible combination of girls and boys to answer the following questions. So we have 3 children. And we know also the independent. So now we'll write all possible combination of girls and boys. So we can have 3 boys, 2 boys, 1 girl, 1 boy, 2 girls, 3 girls, and this like 3, 4, 5, 6, 7, 8 like different possible like outcomes, right? Then what's the first question is, what's the probability of having 0 boys? The only place that we can like find only girls, so having 0 boys, it means having only girls, right? So it's this one. All the rest they have at least like 1 boy, right? So the probability is like in the numerator is the total all ways that we can have 0 boys, which is just 1 way, and the numerator is all possible outcomes, which is 1, 2, 3, 4, 5, 6, 7, 8. So it's 1 over 8. What is the probability of at least 1 boy? So first we'll go here and see at least 1 boy. It's 1 boy or more, right? So this is okay, this is okay, this is okay, this is not okay, this is okay, this is okay, this is okay, this is okay. So it's 7 possible ways, 7 numerator, and again 8 all possible ways. Or we can directly do 1 minus the complement of at least 1 boy. The complement of at least 1 boy is equal to no boy, because at least 1 boy is 1 boy or more. So the reverse thing of 1 boy or more is less than 1 boy, so it's 0 boys, which means no boy. So we can do 1 minus no boy, which is the question we asked, right? The question A, no boy, having 0 boys. So 1 minus 1 over 8, and if we plug here 1 over 8, we'll again find 7 over 8. Then the last question is, what's the probability of exactly 1 boy? So the events where we have exactly 1 boy, the possible ways is this, this, and this. So the possible values are 3/8. Now we'll see another example. Now consider a school with 100 children. Assume that both genders are equally likely, this is important, and the gender of each child is independent of the rest. The first question is, what's the probability of having 0 boys? So the probability of having 0 boys, it is equal of having only girls, like 100 girls, right? And the probability of having one girl is 1/2, like 50%, because they're equally likely. And since they're independent, we will use the multiplication rule, right? So the multiplication rule says 1/2 times 1/2 times 100 times, right? We multiply 100 times 1/2. And instead of writing like the long multiplication, if you like multiply 1/2 1/2 multiplied 1/2, etc., it's like the power, right? So the power, so this is the probability. What's the probability of at least one boy? The probability of at least one boy, it means one or more boy, right? So the complement of one or more boy is the opposite, which is less than one boy. And less than one boy, it means 0 boys, and 0 boys, it means no, like all girls, right? So they can write it as 1 minus the complement, which is probability of no boy or only like girls. This is these two, like the, so these two, no boy or girl, are the same thing. So at least one case. So the complement, like we can write it like this, and this is like this, right? For 100 people. And the last thing is, what's the probability of exactly one boy? So this is, we'll learn this in the next chapter. These are the same. And this is a okay. Now we'll talk about the condition probability. Probability of an event A given B. So the given is important. It's a key word. So the condition probability of A given B. This is how it's like. The given is it is equal to this symbol, and the given, the B, it's the information that we have. For example, if from the previous like if we draw a card, it's the information that previously we had ace, right? And the thing, this is important, the thing that we want to calculate is the probability of A. So we are interested in the blue thing. So we want the blue thing, which is unknown, given the B event, which is known. A isn't known. We want to know, calculate it. B is known. So probability of A given that the event B happened, it's called conditional probability of A given B, right? And it can be calculated as this fraction, where in the numerator is probability A, the intersection of probability A and B, and the denominator is the probability of event B happening. And they can like remember this, like, because this goes over here, and then we write the other parts of the numerator as with an intersection instead of a given sign. Then the conditional probability is the probability of some event A given the occurrence of some other event. So we know that this happened. We want to find the event A. Conditional probability is read as the probability of A given B. It is defined as like here. So remember like this. And we actually I've done this in the previous chapter in the contingency tables, but we didn't like specify that we are doing conditional probabilities back then. So here we see an example with conditional probabilities. So this example says, do male students follow their school's theme more closely than females? Do you remember this example? We had done this example in the past, like in the previous lecture. That's the question. The following data was collected in class on Monday morning after a particular exciting and important basketball game. The question asked was, did you watch the game on TV last night? So I put this conditional probability formula here because we'll use this. And the first question says, find the conditional probability of a student having watched none of the game. So here is the key: game given. Given. Do you remember? Given, it means this. Given now is the information that we have after the given. Given that the student was female. So this is the B, right? We have this information, and what do we want to calculate? The conditional probability of a student having watched none of the game. So none, female and female. We instantly like know that the possible ways is like in this column, because the student has to be female, right here, and we know this, like it's given, and none of it, it's over here. So the possible way, like in the numerator we'll have this, right, instantly, and then the denominator will have the all possible like females, like right here. So here, for a second, ignore these blue things, and there are two ways to calculate this, like conditional probability. So we want to find the conditional probability of a student having watched none of the game given, and the information that we are given is that the student was a female. So we are here, and we want none of it. So we can think like the probability, it will be like the desired outcome for females, which is none of it, is 30 over the total outcomes for females, which is 21 plus 24 plus 30. So it will be 30 over 75. Right? This is what we've done in previous lectures. So we can, the first way is directly through the table. The second way is like using the conditional probability rule, which is the same thing, right? And now I will highlight, just see the highlighting. So the none is this over here, the given is this, which is over here, and the information that we have is here. So we use the conditional probability like formula, and it's straightforward, right? P, probability of none of it and female. None of it and female. So it's 30 over like the total, and the female, the probability of possible outcomes to be a female is 75 over like the total outcome, which 101. Here is 112. So it's the same result, but slower than the table way. And this symbol again it means intersection, or it is equal to and. And the second question is very similar again. Find the conditional probability of a student being. This time is the female is what we want to find, and the given is the yellow again, and the green, which is the known information, is none this time. So the information is the light green. So the information we have is that we know we are here, and we want to find a probability that the person is like female. So it's this, like the possible ways that it will be like female, given that we have the information that none of it was. It's like the possible ways is 30, and we do so like in the previous chapter, we have to divide by the total number of none of it, right? Because if it is none of it, it will be like the rest is like, so the numerator will be 30 because I said y, and the denominator will be the total, like the n, right? And so it will be 30 over 34 directly from the table, or you can calculate it like. So here is the probability way. We can use the conditional probability again. So the given part is the known. This is the information that we have. The given is this. We just want to highlight everything. The symbol. So this is what we want to find. The blue is what we want to find. Being me female. And now let's go to the graph. To the table. We know that we are in the known, and we want the females. So we plug these values again, and we do the conditional probability formula. And over here I used and just to show you that it's the same thing with the intersection. And again, 30 females and none of it. The event, and to find the probability you have to divide by the total possible outcomes, and the same for the non. The total non of it is 34, and the all possible outcomes are 101, so it's 30 over 34, which is the same exact result as the previous. Now we'll talk about independent events and conditional probability. Two events A and B are independent if knowledge about one of event tells us knowledge about one event tells us, so this is given, it means given. The given part tells us nothing about, so this time nothing about the event. So it means that this information doesn't give anything. It doesn't help us to find the blue part. So this is probability of A given B. It is still the probability of A because A and B are independent. So A and B are independent if this equality holds. because then since we don't have any, the information doesn't help, it means the probability remains the same, right, of probability of getting A. And if A and B are independent, then probability of A and B, or the intersection of A and B, is equal with their product. So we multiply probability of A with B, probability of B. So let's see our last example. So first is our last example, and we'll read it now. So random drug testing of air traffic controllers. So suppose the probability that an air traffic controller uses illegal drugs is several over 1000. No test is perfect. But the drug test used here correctly identifies the drug users with probability of 0.96 or 96%. It also correctly identifies non-drug users with a probability of 0.93. So the first question is, the test results are called positive if the test determines the person is using drug, and it's negative if it determines the person is not using drug. Find the following probabilities. Probability of using drug, probability given that is using drug to come positive test, probability given that he's not using drugs come negative, the test comes negative, no drugs, the test comes positive, drugs, the test comes negative. And first of all, we can see that the probability of using the controller using drugs is given over here, is the highlighted yellow part, and then we also have a probability. So here, let's read it. But the drug test used here correctly identifies drug users with probability 0.96. So correctly identifying a drug user, it means that given that he is using drug, the test comes positive. That's the translation. Correctly identified. This is the translation. It's the same like this. The correctly, it means this. And then the other thing is, it also correctly identifies non-drug users with a probability of 0.19. In order to correctly identify non-drug user, it means that the test will be like negative, given that information that we know like he's not like using like drugs. So we have these two like three first values of the probability automatically from the question, and then we can find the other two by the complement rule. The complement rule is like this: the probability of first. Let's see the complement, such as the probability of event A happening given B, it is equal to 1 minus of the probability of event of the complement of the event A happening given the information B. So here this can be written exactly like this, right? Because so the A the complement of the positive here is being negative, right? So we do the same thing, and since we have this green part from here, we just plug it again, and this is called like false negative test, which is yeah. And then sorry, this is false positive, because false positive means that given that he is not, so false positive is given that he's not like using drugs, we are finding it, we are like estimating that he's using, so even though he's not. And false negative is when we are given that he's using drugs, we like predicting that he's not using, so that's false negative. So you do the same thing. So not negative is positive, again not positive is negative. The complements is the same thing, we have all values from here, so we're done with the first question. Then the second question says like, if we tested one non-drug user, what's the probability we get a false positive result? So false positive, we have to know what it means, right? False positive means that given that we know it, right? Non-drug use is given that is no drug user. False positive, it's like predicting like that he is positive, even though he's not, right? He's non-drug user. So this like means false positive. We also like stated in the previous slide, and you can go back. And it is equal to the complement, and it is equal to 0.07. We have this value, right? Then this question C asks us, if 100 non-drug users are tested, find the probability that at least one of them gets a false positive. Again, at least one of them. At least one of them, it means 1 minus none of them, right? Over here you can see it better. So 100 drug users, so the probability at least one, we have at least one false positive result. So we are taking the complement. The complement is 1 minus probability 0 false positives, or 1 minus probability of all 100 tests correctly identifying non-drug users, and this is like 0.93 100 times multiplication. So we are saving space and putting it on the power of this parenthesis, like, and 1 minus this value, and we found this too. Then we have this question D, and the question D asks us to find the probability of test giving a positive result. A positive result, we want like this value, and this looks like familiar, right? It's a condition variable, and first the value that we have is like we found is still in question A. We know that the total is 1, right? Always. So we can easily like find this value. It's 1, like if we sum this and this equals 1, right? So it's the same thing. We do 1 minus this, so this is 0.993, and we'll find the rest now. First, in order to find the first this cell will be equal to the probability since we are in the test positive and drug user, like this row and this column, this means that is equal to probability of being test positive and being drug user. That's because we are in the same in this row and this column. That's why it's translated like this. And this is equal to, so this is the conditional probability formula. I just solve it with respect to the intersection A, B. It's the same like formula. So we write this for this like events exactly the same way, and we have these values from the back. If you go back, you will find this positive and drug user. So it's very clear, and we can find this. We plug this here after calculating. So we found and we plug this here. Then another value that we can find is this one. We are in the row of non-drug users, so here, and we are in the column of test negative. So we want the probability of being non-drug user and being test negative, right? Test like being the test being negative. That's why we use the and again, test negative and non-drug user, because we are in this column, test negative column, and the non-drug user row. So these are all these events that happen at the same time. It's their intersection, right? Again, we use this. So again, we use this conditional probability rule, but we solve with respect to the intersection. We plug these values. We have these values from the previous questions, and we calculate it, and then we plug this here. So we calculate this here and then plug it here. So I didn't calculate it like first. Like, the row will like, and then we'll find the other like. Now we know that this plus this is equal to this. We were missing like this, right? So instead we subtract the total from the drug, this value, right? Because these two, when they add up, they are equal to the total. So we are doing the same thing. We just solve it with respect to this specific cell, right? Because this plus this equals to this. The same thing here. This plus this equals to this. But our unknown is this cell. So we are solving it with respect to this, and we plug this here, the total minus this. Then the same thing, right? We know that this cell and plus this cell is equal to this cell. We add and we find this. We calculate it. Again, the same. The sum of this and this is equal to this total. And we actually calculated the probability that we were asked, right? And it was the probability of a test giving a positive result. We wanted that both, like in both cases, total it's 0.07622. So, or about 8% of all tests will be positive. That's a translation, like that's what interpretation. Then the last question is, find the probability that the person uses drugs given that their test result was positive. So this is given. What do we know? The knowledge that tests are positive. Positive. What do we want to like find? Probably that the person uses drugs. He uses drugs. Drug users. This is again the conditional probability rule. We plug the values, we have everything from the previous questions, so it's 0.09. And this means that only 9% of people whose tests are positive actually use drugs. Those with positive results are not fired automatically. They are given a second, more expensive but more accurate test. And before, like, this is the end of the lecture actually, and this is like a summary that you might need, and you can read like before maybe doing the quiz. So the key things here is disjoint events, and it's good to know all of this. So thank you.